My name is Krzysztof Rzymkowski. I'm a senior engineer here at Snowflake, and I want to talk to you today about text parsing. Let me get straight to the point, because I wanted to do 3 live coding sessions, so I want to cram up a lot of content today. The subject I'm going to work on going to be kind of not trivial, but simple object to parse. It's going to be a Snowflake fully qualified identifier, so let me show you what it is. It's a way, a format that Snowflake uses to identify objects within a schema and a database. So it's 3 identifiers separated by a dot, and each of these identifiers has its rules. Like it can be unquoted, then it's like a variable. It can start with with a capital letter or lowercase, and then some wider range, and it's case insensitive, meaning treat it as uppercase, or you can put it in quotes, then you can put anything inside of it. If you want to escape the quote, use a double quote. So now that you know what it is, these are the examples, like what's the interpretation of them. So if it's unquoted, then it's uppercased and stuff like that. All right. So usually, when faced with text parsings, developers reach to regular expressions to parse it. So raise your hand if you've ever written a regular expression. Yeah, right. At least half of the room or even more. So let's try if that would work here. So taking the parts, the unquoted identifier is kind of easy. There's a range for the first character, and then a bit wider range that is repeated 0 or more times. The quoted one, a bit more cryptic, opening quote, closing quote, and either double quote or not a quote, right? Repeated at least once. So far, so good. I can pipe them together to have the regular expressions for the whole identifier, getting kind of big. But if I try to make the expression for the full identifier, then it looks like the corrupted file. Unusable, cryptic, write once, unmodifiable expression. So it's a dead end. Let's try something different. So the next thing I would try is maybe write a grammar for this format and generate a parser from it. So I'm going to try out Peggy.js because it has this nice playground, and I've used it before. So let's give it a sample valid identifier schema, and let's use the double quotes for 2-inch items. Okay. So here I'm going to write the grammar that describes this format. So top level is fully identifier, and it consists of an identifier, a dot, identifier, a dot, and an identifier, right? So going deeper, an identifier can either be unquoted or quoted. No typos? Quoted, I think so. Unquoted was, we can use the regex now. This was manageable. Z underscore and the wider range. 0 one more times. Quoted one is opening quote, closing quote, and then at least once any char but quote or escaped quote. And the last two, so this was easy. Any char but quote, a regular expression for that, and escape quote is a constant. Cool. So now we have kind of a validator, because the interpreted output is still garbage, but at least it validates now the fully qualified identifiers. to have it extract the information, we need to provide the parser a bit more info. So this is the DB, this is the schema, and this is the object. And I can inject some JavaScript here, return the object DB. Okay, getting better. So next one would be this. Just return the text of the whole expression, and the unquoted one should be uppercased. Cool. And ignore the quotes, take the insights. One last thing, the double quote should be interpreted as a single quote. So there you have it, a grammar that describes the parser going from top down, quite expressive. It can handle really complex syntaxes, like most of the languages have this kind of grammars for the whole language. And usually those generative parsers are quite performant, but there are cons as well. First of all, there's an additional build step, so you need to add it to your pipeline. Then the generated code will probably not be compatible with your linters, prettifiers. It might not be in the language you want it. If you use a TypeScript project, package.js generates JS, so you have to have allow.js configured. And one last con is, I guess, the error handling is not perfect, so let me show you. So it's better than regex, because with regex you have only true or false, matches or not. So this is as much as you could do. With the parser, you get something like this, so a bit more information, but it's still not friendly. I guess what would want something like this, some error messages that tell me precisely what needs to be fixed. So I think we can get rid of all those cons writing a custom parser. And I can show you that it's going to be almost as readable as a grammar without the cons of generating code. So let's go. So I got this a bit of starter code. So the top level was fully qualified identifier, and it's an identifier followed by a dot, and repeat it, and the end of input. Okay, let's start with the simpler ones. The dot. So I'm going to go down and down with the methods describing all the parts that the object-oriented parsing consists of. So I have this small abstraction of the input stream that has the accept method that takes a prefix. If it matches the input, then it returns true and moves the input by the match. And if it doesn't match, it returns false. So with it, I can do quite a lot. So here, I'm looking for a dot. If it's not a dot, then it's an error. So I got this error messages listed in the errors so that I don't need to write them whole. Okay, next one, let's go with the end of file. So now, if I get any input, so this is a regular expression for anything, coincidentally a dot as well, then I'll throw expected end of file. Okay, the interesting one, the domain specific identifier. So identifier is either unquoted, come on, or quoted. And if it's neither, then it's there. Otherwise, return it going down, unquoted. Here we can use the expression if it matches the same regex. I'm not going to write it more times. So if it matches this regex, then return the last match that the Elixir stores in the current symbol method. Otherwise, return undefined and quote it. So first of all, if it does not start with a quote, it's not a quoted identifier. Otherwise, we're going to collect its value. So we can have not a quote. Then we just add it to the value. We can have a double quote. Then we add a single quote. Then we can have a single quote that will close the identifier, so we break up the loop. And if we either didn't get the quote or not a quote, then this must be end of the input. So this is the missing quote error, missing closing quote. The loop is endless, only taken by the break. Here we can check if it's not empty. And return it. All right, let's see what I missed. All right, yeah. At the first, we need to tell it that this is the DB. This is the schema. And this is the object. And return the structure that I expect. Okay. So that was better, but now, yeah, uppercasing. If it's unquoted, it needs to be unquoted, needs to be uppercased. And that's all green. So this is the parser that does the same stuff, even better than the generated one. Still very readable. We still can follow it top down with each method corresponding to each level of the format. So actually, this method is more or less called recursive distant parser, and it's not the only method you can write a parser. There's also one kind of even more beautiful called parser combinator, and I'm gonna try to squeeze it with this one more. Let's get started from the beginning, from the top. Okay, so with parser combinators, the idea is a bit different. You take small parsers and combine them together to parse different stuff. So a parser is basically a method that takes the input string and returns a result. The result can either be success, that has the interpreted value and the rest of the input that is outside of the scope of this parser, or a failure result that has the error context. With this, you can build simple parsers. For example, this is a parser creator function that will create a parser that matches the prefix. So if the import starts with this prefix, it's a success. Otherwise, it's a failure. And with these simple parsers, we can build a full grammar. So there are, I got this small library of generic parser operators like sequence that takes an array of parsers and invokes them one after another. If all succeed, the result is the array of these values. If any of them fail, it's a failure of the first one. So I know that the fully qualified identifier is then the sequence of identifier parser, a terminal dot, so dot, right? A dot and a generic end of file. Identifier is either still generic parser combinator that takes parser and invokes up until the first one succeeds. So it's either unquoted or quoted. Unquoted will use a pattern, still generic, and the regex. And unquoted is a bit more complex. It's a sequence of the opening quote, closing quote, and inside we have one or more generic of either not a quote, so I'll inline the pattern here, not a quote, or an escape quote. And the last one, so this is a terminal of double quotes. Okay, almost there's some type error still, because the generic parsers don't really know what to do with the values. They can only return, like sequence can only return an array. But we know the quoted identifier is a single string. So the convention is that the second method of each parser is the mapper function. So here I'm gonna join all the values. The same goes for one or more. Now the types are fine, except I still need to tell how to extract the DB schema and the object. So here I use array deconstruction as the argument. First one is the identifier, so it's the DB. Second one is the dot I can ignore. Then goes the schema, the dot ignore, and the identifier and the object. So it's DB schema object. Let's see what I missed. Again, uppercasing. So I'm going down. Identifier unquoted here. And can you see what the last thing I missed? Oh, it's two things. Like this is the interpretation, the definition of the format. Like the doc says, if it's unquoted, then just it's case insensitive. It should be uppercased. So first one is here. The double quotes inside the quote are interpreted as a single quote, and the other one is we should skip the quotes. They are interpreted as nothing. Some spaces. And it should be green, right? So this is in pure JavaScript, something that looks almost as the grammar for the parser generator. No code generation, as readable. You can follow it with code navigation. This parser combinator for you. So I made it in time.
Impressive. Thank you.
Thank you.
I'll try. How does that perform on production? Because every solution uses regex. Regex is pretty slow. So how fast is this solution in the end?
So for this kind of input, when we expect maybe 100 characters, it really doesn't matter what we use. The operations here I might have sometimes not used like small parsers that do combinations. But generally, on this kind of input, all the parsers, the regex, the combinator, and the recursive descent were more or less the same, milliseconds for a few examples. I'm guessing if performance is really important for you, use the parser generator. It's going to be, there's more engineering effort put there to make it more efficient on the input.
Hi, I loved your breakdown of all the different solutions. I wonder what was the real story? How did you, end up on the final solution?
Actually, the final solution right now we're using is the destined parser that I wrote when I saw like in existing code and not perfect interpretation of the like kind of buggy interpretation of the fully qualified identifier. So I saw it was buggy. It was trying to split by dot, not taking into account the dots inside the quoted and stuff like that. So I sat down and wrote the more or less destined parser because I remember it from the book by Björn Strastrup on C++. There's the first full example of a program is actually calculator that does input parsing. So I remember this construct from way back, and I knew it can write a nice parser. And then while preparing for the talk, Michał Piotrkowski, a friend of mine from Snowflake, pointed me to parser combinators that's even better, even nicer. Though I wanted to show you both because I think the first one is a bit more easier to digest. The other one is like higher order functions, so like good to note both.
I have two questions. One is if you could once again explain difference between second approach and the third one, the two parsers. I didn't quite get it, like high-level description of solution. And the second question is, what editor do you use?
This is IntelliJ IDEA. Or Webster
Okay.
would be the same, but IntelliJ has more languages. Okay, so the recursive destined parser uses methods. Yeah, it's more imperative. You execute the order of method execution, like defines the order of elements in the input. Each part has its own method that will return success if it matches or backup if it does not. And so it's kind of loosely based on recursive destined parsers, kind of maybe a bit optimized for this solution. The other one builds a parser, kind of declarative by joining functions. So now you have a parser object that is declaratively built using higher order functions. And then you can just run it on the input. Like this is more functional. That one was more imperative, though. You can still do this one in an object-oriented language with all those operators as objects.
Okay, another question.
Yeah. Thanks. Very good talk. My question is, do you maintain the same rules over different platforms, languages?
Do you maintain what? Different?
Like, you should build the same rules over different languages and platforms, right?
Yeah, so generally this is not, in a functional language like JavaScript, it's easier, it's concise to write this kind of a parser composer. But the ways of writing this parser are language agnostic. You could write those in other languages in a more or less similar manner. Did this answer your question? I don't see you're convinced. Okay, catch me after the talk. We'll talk more.
Yeah, you're staying with us, right?
Yeah, until the end.
Yeah, feel free to talk to the speaker. That's how you network. Okay, I saw there's one more question. Let's do that. We still have time. I hope you still have the power to answer more questions.
Yeah.
Thanks.
So how do you handle grammars with preferences, like precedence and the recursive destined approach?
Yeah, I didn't have to actually have this problem because I didn't get to point of getting like a huge language or like a weird language. Like I know Michał used it for parsing SQL for mocking in tests. So he interprets SQL, it worked fine. There's most of the forpaths are actually rather easy to, you don't need to go the backup. But it's, yeah, I would need to dig into that more.
Do we have any more questions? Okay, there's still time. So I'll pop one, if you don't mind. In regular expressions, you need to worry about lookbacks. Do you have any big performance risks, like things that you should avoid doing because they're risking expanding the complexity that you want to warn people about?
Yeah, so it's similar in this parsers. You can have either a lot of combination going in deep into the method calls, and then they need to back up, or a lot of parsers are getting called and returning failures up the chain. The order of either parsers might make a difference. It's actually kind of easy to debug these parsers. You can put a breakpoint and or instrument those methods and see which one is taking most. So it's easier than with a parser generator that like it spews out some code. You cannot see which method is taking the longest. I don't have a perfect answer for you, but this is what I would try first.
Oh, this is a very good answer. Okay, I don't see any more questions. Thank you. This was great.
Warsaw.